The universe is vast and mysterious. It's full of wonders that we are only beginning to understand. Black holes with their immense gravity continue to fascinate us. Neutron stars, denser than you can possibly imagine, challenge our understanding of physics. And then there are wormholes, these theoretical tunnels that could connect different points in space and time. Imagine traveling vast distances across the cosmos in an instant. It sounds like science fiction, but the idea is rooted in real science. Albert Einstein revolutionized our understanding of gravity with his theory of general relativity. He showed us that gravity is not a force acting over a distance. Instead, it's a consequence of the curvature of space-time. Massive objects create dips in this fabric, and other objects follow the curves created by these dips. This is what we perceive as gravity. Einstein's equations, however, also allowed for some rather bizarre possibilities. One of these was the concept of wormholes. The idea of wormholes as shortcuts through space-time is incredibly alluring. Imagine being able to travel to distant galaxies in a fraction of the time it would take using conventional means. The vast distances between stars and galaxies have always posed a significant challenge for space exploration. Current spacecraft would take tens of thousands of years to reach even the closest star systems. Wormholes, if they exist and are traversable, could potentially allow us to overcome these limitations. It's a possibility that fuels our imaginations and drives our curiosity about the universe. Wormholes have captured the imaginations of many, often appearing in science fiction literature and films. These stories often depict wormholes as gateways to other dimensions or as a means of time travel. While these depictions are entertaining, it's important to separate science fiction from science fact. The wormholes we discuss in astrophysics are based on our current understanding of general relativity. However, even within the realm of theoretical physics, many questions and challenges remain. One of the biggest questions is whether wormholes are stable enough to traverse. A cosmic conundrum, delving into wormhole types. Just like there are different types of stars, galaxies, and even black holes, theoretical physics suggests there might be different types of wormholes. Each type comes with its own set of properties and characteristics, some more outlandish than others. Imagine trying to understand a new species of animal. You'd want to know about its behavior, its diet, its habitat. Similarly, physicists are trying to understand the potential behavior of these theoretical wormholes. One of the most crucial distinctions lies in their traversability. Could a spacecraft actually travel through these cosmic tunnels? Some wormholes, like the ones we often see depicted in science fiction, might allow for two-way travel, acting as intergalactic shortcuts. Others, however, might be more like one-way streets, allowing passage in only one direction. Schwarz wormholes, a one-way ticket. Let's start our exploration of wormhole types with the Schwarz wormhole, named after the physicist Carl Schwarzschild. This type of wormhole arises from the mathematics describing a non-rotating spherical black hole. Imagine it as a simple symmetrical tunnel through space-time, connecting two different regions of the universe, or even two different universes altogether. However, the catch with Schwarzschild wormholes is their instability. They are theorized to collapse incredibly quickly, potentially faster than the speed of light. Traversible wormholes, keeping the doorway open. Now let's shift our attention to a more intriguing type of wormhole, the traversible wormhole. As the name suggests, these theoretical objects hold the tantalizing possibility of being stable enough for a spacecraft to journey through. Imagine a cosmic tunnel that remains open, allowing for two-way travel between distant corners of the universe. But here's the rub. Keeping a wormhole stable and traversable requires a special ingredient, something physicists call exotic matter. This isn't your everyday matter, like the stuff that makes up stars and planets. Exotic matter is theorized to have negative mass-energy density, a concept that sounds like it's straight out of science fiction. Section 4. Exotic matter and negative energy, the keys to stability. The concept of exotic matter and negative energy might seem like something out of a science fiction novel, but it's a serious area of inquiry in theoretical physics. Scientists are delving deep into these concepts to understand their potential implications for the universe. According to Einstein's theory of general relativity, which has been incredibly successful in explaining gravity, the fabric of space-time can be warped and curved, not just by massive objects, but also by energy. Think of a trampoline. This warping is what we perceive as gravity. If you place a bowling ball on it, it will create a dip. This dip represents how a massive object like a planet or a star can warp space-time around it. That's like a massive object warping space-time. The more massive the object, the deeper the dip, similar to how black holes create intense warps in space-time. But you can also make the trampoline dip by pushing down on it with your hand. This demonstrates how energy, not just mass, can influence the curvature of space-time. That's analogous to energy warping space-time. Energy in various forms can have a significant impact on the structure of the universe. Now imagine a strange type of energy that instead of pushing down, pushes the trampoline upward. That's negative energy. This concept challenges our traditional understanding of physics and opens up new possibilities for the nature of the universe. Section 5, A Bridge to Where? The Allure of Traversible Wormholes. The possibility of traversable wormholes, however distant it might seem, ignites our imaginations and fuels our desire to explore the cosmos. Imagine a future where spacecraft could zip through these cosmic shortcuts, bypassing the vast distances between stars and galaxies. It would revolutionize space travel, making it possible to reach destinations that currently seem hopelessly out of reach. Think about the early explorers who set sail across the vast oceans, driven by a thirst for discovery and a desire to connect with new lands and cultures. Traversible wormholes could be the ships that carry future explorers to distant star systems, allowing them to unravel the mysteries of the universe and perhaps even encounter other civilizations. Section 1. The Paradox of Stability. Can wormholes stay open? Imagine a bridge that flickers in and out of existence, here one moment and gone the next. That's the challenge with wormholes, at least according to our current understanding of physics. The very fabric of space-time, as described by Einstein's theory of general relativity, seems to conspire against the stability of these cosmic shortcuts. It's like trying to prop open a doorway in a house of cards. The slightest disturbance could bring the whole structure tumbling down. The intense gravitational forces at play near a wormhole's throat, the narrowest point connecting two distant regions of space-time, are thought to be incredibly powerful, potentially causing the wormhole to collapse faster than the speed of light. Section 2, Exotic Matter, Fact, Fiction, or Physics Fantasy. Exotic matter, the hypothetical substance often invoked as a potential stabilizer for wormholes, is a mind-bending concept that pushes the boundaries of our understanding of the universe. Imagine a substance that, instead of being pulled by gravity, is actually repelled by it. It's like holding a magnet near another magnet and watching them push each other away instead of attracting. This peculiar property of exotic matter arises from its theorized negative mass-energy density. In the familiar world of everyday experience, mass and energy are always positive. Section 3, the energy dilemma, fueling a cosmic shortcut. Even if we could somehow find or create exotic matter and use it to prop open a wormhole, the energy requirements for such an endeavor would be astronomical, literally. Imagine trying to move a mountain from one place to another. It would require a tremendous amount of energy. Now imagine trying to bend the fabric of space-time itself, creating a tunnel through the cosmos. The energy scales involved would be mind-boggling. Some physicists have estimated that the energy required to create and maintain a traversible wormhole could be equivalent to the total energy output of a star over its entire lifetime. Section 4, Through the Looking Glass. Wormholes and time travel wormholes, with their potential to connect distant regions of space-time, have captured the imaginations of science fiction writers and physicists alike. These fascinating structures, often depicted as tunnels or bridges through space, offer a tantalizing glimpse into the possibilities of the universe, particularly for their implications for time travel. The concept of moving through time as easily as we move through space has long been a staple of science fiction, but wormholes offer a theoretical basis for such journeys. If we could somehow traverse these cosmic shortcuts, could we also journey through time, visiting the past or glimpsing the future? This question has intrigued scientists and dreamers for decades. The idea of wormholes as time machines is deeply rooted in Einstein's theory of general relativity. This groundbreaking theory revolutionized our understanding of space and time, showing that they are interconnected in a four-dimensional fabric, which suggests that time is not absolute but is relative to an observer's motion and the gravitational field they experience. This means that time can stretch or compress depending on the conditions. Imagine two clocks, one placed at sea level and the other on a mountaintop. This simple thought experiment illustrates the profound effects of gravity on time. Because of the difference in gravity, time will actually move slightly slower for the clock at sea level. This effect, though minuscule in everyday life, becomes significant in extreme conditions such as near a black hole, a phenomenon known as gravitational time dilation. This concept not only deepens our understanding of the universe, but also fuels the imagination of what might be possible in the realms of time travel and beyond. The idea of time travel, particularly the possibility of traveling to the past, is rife with paradoxes that challenge our understanding of cause and effect. One of the most famous thought experiments illustrating these paradoxes is the grandfather paradox, which highlights the potential for logical inconsistencies when considering time travel to the past. Imagine a scenario where you build a time machine and decide to travel back in time to meet your grandfather before he met your grandmother. Now imagine that in a fit of misguided mischief, you accidentally cause an accident that prevents your grandfather from ever meeting your grandmother. What happens next? The grandfather paradox and other similar thought experiments have led physicists to grapple with the concept of causality, the relationship between cause and effect. In our everyday experience, we observe a clear order of events. A cause precedes its effect. You flip a switch, the light turns on, you drop a ball, it falls to the ground. But time travel, particularly to the past, throws this seemingly fundamental principle into disarray. If we could travel back in time and alter the past, wouldn't that violate the principle of causality? Humanity's fascination with the cosmos is deeply intertwined with a longing to explore its vast expanse. Yet the immense distances between stars and galaxies, measured in light years, pose a formidable barrier to our cosmic aspirations. Even with the fastest spacecraft imaginable, journeys to even the nearest star systems would take thousands of years, far exceeding a human lifetime. This is where the concept of wormholes, those theoretical tunnels through space-time, ignites our imaginations. What if we could bypass the limitations of conventional space travel, circumventing the vast cosmic distances by taking shortcuts through these cosmic tunnels? Imagine folding a piece of paper in half so that two distant points touch. A wormhole would be like punching a hole through those points, creating a shortcut between them. Section 2. Cosmic highways, navigating the maze of space-time. Imagine a network of cosmic highways crisscrossing the universe, connecting distant galaxies like intergalactic superhighways. That's the tantalizing vision that wormholes offer, transforming the vast, seemingly empty expanse of space into an interconnected web of cosmic destinations. But navigating this cosmic maze wouldn't be as simple as plotting a course on a star chart. Unlike traditional space travel, where trajectories are determined by gravitational forces and orbital mechanics, navigating wormholes would require a deep understanding of the geometry of spacetime itself. Section 3. Fueling the journey energy considerations for wormhole travel. Even if we could overcome the technological hurdles of creating stable wormholes and navigating the cosmic labyrinth they create, we would still face the daunting challenge of fueling such extraordinary journeys. The energy requirements for wormhole travel would likely dwarf anything we can currently comprehend, pushing the boundaries of physics and engineering to their limits. Imagine trying to compress the entire mass of the Sun into a space the size of a sugar cube. That's the kind of energy density we might be dealing with when manipulating space-time to create and maintain traversible wormholes. It's like trying to power a city the size of Tokyo with the energy of a single lightning bolt. Section 4. The Starship Designer's Dilemma: Building for the Unknown. Building a spacecraft capable of withstanding the rigors of wormhole travel would be an engineering challenge unlike any other. Imagine designing a ship that can withstand the crushing gravitational forces near a black hole, navigate the turbulent eddies of spacetime, and emerge unscathed on the other side. Traditional spacecraft are designed to operate in the relatively benign environment of our solar system. They are built to withstand the vacuum of space, the radiation of the sun, and the occasional micrometeoroid impact. But a wormhole-faring vessel would need to be far more robust, capable of resisting forces and environments that would tear apart conventional materials like paper. Section 5. Safety first. The perils of wormhole navigation. Venturing into a wormhole would be like navigating uncharted waters, fraught with unknown dangers and unforeseen perils. Even if we could create stable wormholes and build spacecraft capable of withstanding the journey, the act of traversing these cosmic shortcuts would be a perilous undertaking. Imagine entering a tunnel with no guarantee of what lies on the other side. The wormhole could collapse unexpectedly, crushing the spacecraft like an aluminum can, or it could lead to a region of space teeming with deadly radiation or other unknown hazards. Section 6. Ethical considerations. The responsibilities of cosmic explorers. The prospect of wormhole travel raises profound ethical considerations that extend beyond the technical challenges of physics and engineering. If we were to master this technology, we would be stepping into a new era of cosmic exploration, one that comes with a weighty responsibility to safeguard the universe and its inhabitants. Imagine encountering intelligent life on a planet reached via a wormhole. What would be our protocols for interaction? Would we risk contaminating their world with our presence, or conversely, risk contaminating our own world with something brought back through the wormhole? Section 7. A new era of discovery. What awaits us on the other side? The prospect of wormhole travel is a potent reminder of the vastness of our universe and the endless possibilities that lie beyond our current reach. If we can unlock the secrets of these cosmic shortcuts, we will open the door to a new era of discovery, one that could reshape our understanding of the cosmos and our place within it. Imagine standing on the surface of an alien planet, gazing up at a sky filled with unfamiliar constellations, breathing air with a different chemical composition, feeling the pull of a different gravity. Wormholes could make such experiences a reality, allowing us to explore worlds beyond our wildest imaginations. The study of wormholes, these theoretical tunnels through space-time, does more than just stretch the boundaries of our scientific understanding. It challenges our very perception of reality and the fundamental laws that govern the universe. It compels us to re-evaluate our place in the grand scheme of the cosmos, urging us to consider the profound implications of such phenomena. For millennia, humans have gazed up at the night sky, awestruck by the countless stars and swirling galaxies, pondering our connection to this vast and mysterious universe. Are we alone? This question has driven our curiosity and exploration for generations. Are there other worlds out there, perhaps harboring life as we know it or life as we can't yet imagine it? The discovery of exoplanets has only intensified this quest, revealing a universe teeming with possibilities. Wormholes, while still firmly in the realm of theoretical physics, offer a tantalizing possibility. A cosmic shortcut that could allow us to breach the immense distances between stars and galaxies, potentially revolutionizing space travel and our understanding of the cosmos, transforming our perception of the universe from a vast and impassable gulf into an interconnected web of possibilities. This interconnectedness could redefine our approach to space exploration, making the dream of interstellar travel a tangible reality. The human spirit is driven by an insatiable curiosity, a deep-seated desire to explore the unknown, to push the boundaries of our knowledge and understanding. From the earliest explorers who set sail across uncharted oceans to the astronauts who dared to venture into the void of space, humanity has always sought to expand its horizons to discover what lies beyond the next mountain range, the next ocean, the next celestial body. Wormholes, in a sense, represent the ultimate frontier, the ultimate challenge to our spirit of exploration. They dangle the possibility of reaching out to distant corners of the universe, of encountering new worlds, new life forms, new civilizations, perhaps even uncovering the secrets of the universe's origins and its ultimate fate. Section 3, the universe as a teacher, humility in the face of the unknown. The study of wormholes, with its mind-bending concepts and seemingly paradoxical implications, serves as a powerful reminder of the vastness of our ignorance. For all our scientific advancements, for all the knowledge we've accumulated over centuries of inquiry, we are still like children peering through the keyhole of a vast and mysterious mansion, catching only fleeting glimpses of the wonders that lie within. The universe, in many ways, is a humbling teacher. It constantly challenges our assumptions, forcing us to confront the limits of our understanding. Just when we think we've grasped the fundamental laws of nature, a new discovery emerges, a new mystery unfolds, pushing us to reevaluate our place in the grand scheme of things. Section 4, the power of imagination. From science fiction to scientific inquiry. The concept of wormholes, once relegated to the realm of science fiction, has taken root in the fertile ground of theoretical physics, inspiring generations of scientists to grapple with its mind-boggling implications. It's a testament to the power of imagination, of our ability to envision possibilities that extend beyond the limits of our current understanding. Science fiction often serves as a precursor to scientific discovery, planting seeds of inspiration that blossom into groundbreaking research and technological innovation. Jules Verne's fantastical tales of submarines and voyages to the moon paved the way for the development of submarines and space travel. H.G. Wells's The Time Machine sparked imaginations and fueled discussions about the nature of time and the possibility of manipulating it. Section 5. A future shaped by curiosity. Investing in the frontiers of knowledge. The pursuit of knowledge, particularly in fundamental areas like wormhole physics, is an investment in our future. While the practical applications of such research may seem distant or even impossible, the journey of discovery often leads to unexpected breakthroughs with far-reaching implications. Consider the development of the Internet, a technology that has revolutionized communication, commerce, and countless aspects of modern life. The Internet's origins can be traced back to fundamental research in computer science and networking, research that had no immediate practical applications at the time. Section 6. Our Cosmic Legacy, a Universe Waiting to be Explored. As we stand on the cusp of a new era of space exploration with ambitious plans to return to the Moon, establish a presence on Mars, and send probes to the icy moons of our solar system, the study of wormholes serves as a potent reminder of the vastness of the cosmos and the countless wonders that await us beyond the horizon. The universe is our cosmic legacy, a vast and mysterious realm beckoning us to explore its secrets. It's a realm of swirling galaxies, exploding stars, black holes warping the fabric of space-time, and perhaps even other universes, hidden from our view but connected to our own in ways we are just beginning to comprehend.